does. It sounds pretty nice. Okay, good morning, folks. I put out an email a little while ago with 3 different announcements in it. The first announcement is that there is a weird linker error that you see every once in a while. And the weird linker error has something to do with an out-of-range assembly language jump related to a floating point multiply. Nothing you should have to deal with. The fix for it is explained in item 14 of the C gotchas on the debugging page. I gave you a link in the mail. I'm not going to go through it, but basically you have to add one library in the linker and then it's fixed forever. I also put in the mail half a dozen or so different possible voices that you could use, or parameter sets that gave reasonable sounds. You're not limited to those. You don't have to use them. Thought you might like them for reference. The third announcement is that I have to be gone tomorrow and Friday, and so the Friday lecture will be in lab. There will be no lecture. You get extra time to work in lab, starting at 10 on Friday and going through until 4:30, no break. Yippee! Obviously, the whole class will not fit in the lab. It's first come, first serve in the morning. And in the afternoon, of course, Friday lab gets preference, and it's a big lab. Yes? Will there be a lab section on the weekend? I haven't heard back from Human yet. I expect that there will be. Keep track of the mail. I won't be able to modify web pages after today, so unless he gets back to me today, it won't be on the web page, but it will be on Facebook and in mail. Yeah.
And also, Friday group will be required to be in its section.
Yes, just because you come in the morning, and if you're in the Friday group and you come in the morning, you still have to be there in the afternoon. I brought along a slightly modified but working version of a stochastic synthesizer here. It's a 2-voice implementation. It's slightly modified in that the user interface is designed for a 3-year-old because I'm building it for my granddaughter. And so there's no sort of numbers and LCD readout, but that doesn't make it easier to use exactly. It makes it different. So I thought I'd play it a little bit. There's two. So there's 2 voices playing four notes and then stopping, and the other voice plays 4 notes. They can play together. They're just not set up to do that. I'll set them so they play together. Sure, I will. They're playing together now. So there's 2 independent sounds being added together. Now let's go back to the default configuration. We can change each voice also to a different timbre. I'm overdriving these little speakers. I wouldn't say that's actually a useful tone, but it's kind of a weird bass line. And this is supposed to be kind of bell-like. Okay, so your implementation should just play on forever randomly, or in a Markov sense. And in this implementation I'm asking you to do, you do not have to impose a beat structure. It can just play continuous notes. But you do have to be able to implement different parameter sets for different timbres on command. Any questions about that? In building the debounce state machine, I found an interesting thing, and that was I couldn't get the state machine out of state 1, which was possible button down. And the reason was that pin C, the built-in variable pin C, which is documented as being an 8-bit int, returns a 16. And then so when you say tilde pin C, and let's say there's no buttons pushed, you return tilde pin C and you get 0xFF00. Oh man, no wonder it doesn't match FF. So I don't remember seeing this before, but in any case, if you mask a 16-bit value with an 8-bit mask, and with an 8-bit mask, it fixes it, obviously. And another hour of my life disappears debugging that. Any questions about Lab 3? Okay. There's one last little piece of code that I didn't get to last time, and that was in the interrupt service routine. The last thing you have to do is to check and see if main has signaled that a new note should start. And the new note starting starts the dynamics of the decay and the rise and the fall and all that. So there's some start time here. And the variable I used to represent that was, I called it pluck. And that was because I was thinking about strings initially. But it's some sort of trigger that says set t equal to 0 for all of the exponentials. So what does that mean? We're going to have some, if pluck equals 1, then we're going to need to set the amp of fall main to its maximum value right here at the top of the exponential, and that's going to be some max amp, which you're going to choose so that nothing overflows. And rise phase main gets set to max amp. Remember that the rise and fall is the product of a rising exponential and a falling exponential. So we have to start off the rising phase, and just to make certain that I had all the initial conditions correct, set amp rise, not rise, rise to 0, and amp FM to max amp, because the FM amplitude, the FM modulation amplitude, is a continuously decaying exponential, just like fall main. And in the original code, oh, and then we have to set pluck equal to 0. That satisfies the handshake condition back with main. And originally, I phase locked the two phase accumulators by setting ACC main to 0 and ACCFM to 0 in here. But this was a bad idea. Why was it a bad idea? Turns out it's subtle. But the reason is that if you set the phase back to 0 when you start a new note, then if the voice is still playing the last note, because after all it's exponential decay, it might still be playing, then you get a phase discontinuity in the note. And the phase discontinuity means there's an instantaneous jump in amplitude and therefore a click. And so the thing clicked hideously. Pop, 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 pop on every note transition where the note had not died away before the next note started. Eliminating the phase reset eliminated the phase jump. And so it sounded much cleaner. Surprised me. Yeah.
What was setting amp fall main and phase main max amp? Do you factor max amp squared?
Yes, but remember that you're doing those weird shifts by 8 in the multiplies. So it renormalizes everything. Divides it by 2 to the 16th. So for every different voice, you're going to have a different pluck. You have pluck 1 and pluck 2, whatever you want to call them. But you're going to have two separate variables, one to say when voice 1 plays and another one to say when voice 2 plays, unless they always play at exactly the same time, which seems unlikely. Any questions about that?
Relate those variable names to the Dix and Stein equation that we had written out.
So going back, there were 3 equations. One was the FM. There was a differential equation. Well, let's go back and write out that we're going to consider the amplitude to be some tau rise process and some tau fall process, and we're going to write this as A0 e to the minus t over tau fall times 1 minus e to the minus t over tau rise, right? That's that form. And at t equals 0, we want this exponential to be at a maximum, so we set this to max amp. This term is at max amp. We are going to decay this from max amp, and so we do exactly the same thing here. And this is not 1 now, but this has the value in the equation of max amp. So we're initializing exponentials, which is the same as setting time equal to 0 for the new note. Did I answer what you asked? Or close? Okay. Any other questions about this? The synthesis code is fairly abstracted differential equations. One group came up with the clever idea of saying, well, we're simulating these differential equations as shifts and adds. There's only something like 6 different values for time constant, which are all powers of 2. Why not just build a table? Don't solve the stinking equations, just build a table. So you trade off CPU time for your intelligence. Or for MATLAB's intelligence, anyway. So that's an interesting trade-off. There's one last thing that I've been promising to talk about and haven't, and that is debouncing the keypad. Is this still relevant, or has everybody else figured out already how to debounce the keypad? You've all figured it out. And you can build a string directly while debouncing. Let's say you want to input an FM frequency as a parameter, 150 hertz, 150. Can you say 150 enter? Does anybody need that? You need that. Okay. Let's talk about it then. So something is going to request a string. There's going to be some human is going to do some action, or there's going to be something that cues the keyboard task that a string is required. And so there's going to be some entry point where a task wants a string, and you're going to enter into some state in which hopefully the silly user won't be resting their hand on the keypad, and the keypad will be in the release state. So we're going to enter in the release state. This is not where we enter at reset time, however. We'll talk about that in a minute. In the release state, remember the variable button. That's the button which is returned from the key scanner. If it has a value of 0, either no button is pushed or an invalid combination of buttons is pushed. So we ask, is button equal to 0? If the answer is yes, we return here, and of course we call keypad again. Let me do a little annotation before I get too deep in this. First of all, every single transition in this state transition diagram, every transition is going to call keypad. So I may not write that out anymore to save a little bit of time. But there's going to be a few state variables. One is key count, which is going to keep the number of characters which are currently entered in the string. There's going to be key string, which you might guess is the actual string. And there's going to be key ready, which signals the task who wants the string if the user has pressed enter. In other words, they've pressed the terminator key and terminated the string that they're entering. All right, if the answer to this is no, then we must have pressed a key. Nope, it's not 0. And so we're going to take some variable called maybe, it may be the key, and set it equal to button. So maybe is going to be the value of button at this state. We call keypad again. We get into debounce. debounce press, and we ask, does but num equal maybe? If the answer is no, then probably the button is still bouncing. State transition time. Equals 30 milliseconds. If the answer is no, call keypad again and repeat. If the answer is yes, then we have to go to a state called detect terminator. Works through Skynet. And in the detect terminator, we ask, does maybe equal the terminator? Whatever it is, A, B, C, D, whatever key it is you decide to use on the keypad. And if the answer is yes, then we are done. Oh, we also have to set key ready equal to 1, and we may have to terminate the key string of key count equals 0. May have to terminate that. And the done state has no test and never exits. It's an absorbing state until the next request from outside for a new string. Yes? Key ready equals 1. Key ready equals 1, and key string of key count equals 0. At reset, we enter here. Well, what if it's not a terminator? What if it's just a normal character? In that case, we need to say key string of key count plus plus equals but num. And if you want to convert this to ASCII, you may have to do some manipulation here. You may have to add a constant to but num, but I'm not going to talk about that right now. And then we have to go to a state still pressed. Yes, that's still pressed. Yes. And again we ask, is but num equal to maybe? If it is, we call keypad and go back to that state. If the answer is no, then we're going to do a debounce release. Call keypad again and ask, is but num maybe? But num, B-U-T-N-U-M, equals maybe. If the answer is yes, we go back here. If the answer is no, we go here. So when key ready is finally set, there is a 0 terminated string in key string. And if you've manipulated button properly, then it will be an ASCII string that you can submit to scanf or some other conversion utility which converts it to an integer. Or you can do the conversion yourself. This interlocks the keypad so that you get exactly 1 digit per press. You get exactly 1 digit per press, and you detect a terminator, an enter key, to finish the operation and tell the interpreter that it's time to convert to a number and feed the number off to whatever needs it, some parameter setting function. So it's not much harder than just debouncing one key, one button. Instead of 4 states, we've got 1, 2, 3, 4, 5, 1, 2, 3, 6 states, one corresponding to a boring absorbing state. And the only additional one is we have to detect a terminator because there is one special key on the keyboard that finishes everything, and the rest are interpreted as members of this, as adding to the key string. Questions? So this allows us to enter something like 153, enter, and button you hope is going to return a 1, a 5, and a 3. You can make it do that. You can make button map to the digits rather than the physical positions on the keypad by reordering the lookup table any way you want. To make these into ASCII characters, what do? What is the value of the string of the character 1? Pardon me? 49, I think that's right. No. 48 is an A, right? 48 is 0. Hexadecimal 30. Hexadecimal, that sounds right. So you have to add a hex 30 to each of these numbers. So if you were to add button here plus 0x30, then what would be stored in key string would be exactly an ASCII string, which is exactly what scanf needs as an input to produce an integer as an output. I think there's also string to int functions in standard lib, if you prefer those to scanf. So every 30 milliseconds, you're going to call keypad. You're going to call the function keypad, which is going to return button. So every 30 milliseconds, you're going to poll keypad, it's going to return button, and you're going to pass through this state machine.
So is this going to be like encapsulated in some sort of like function? Are you like stuck in here, or is this executing like asynchronously?
No, you're not stuck in here. The signal here tells some other function that you have a ready result.
You should pull that key ready
Yeah, you have to pull the key ready in some other function. Right, yeah. I suppose you could use key ready to throw a software interrupt. But why bother? There's some things that's just not worth putting in an interrupt. And this doesn't require much time. It's not blocking. And so it's going to take a few microseconds to read the keypad, fall through the state machine, and get back out again out of the task. So it's hardly worthwhile writing an interrupt to run the state machine. You could. Questions? Any more questions about a synthesis or Lab 3 in general? Yeah?
And here the length of each note can be just fixed, like 1 second, 1.5 seconds.
You can fix the length of the note. 1 second's a little slow. Let me show you what 1 second sounds like. This is 1 second. Might be good background music when you're trying to go to sleep or something. This is 8 a second. That's a little ridiculous. 4 seconds, not bad. So we can change voices again here. And I say I'm not sure this particular voice is useful. But I like this bell-like thing. So it should just play on. It should just go on forever, aimlessly, never resolving. Sort of like Markov elevator music. Markov's elevator. Takes you to a random floor. Never mind. What?
Are we supposed to edit parameters while it's playing?
Edit parameters while it's playing. Why not? I don't see any reason why not. There's plenty of time, because while the note requires an 8,000 per second interrupt, main can run relatively slowly and still get done what it needs to get done in terms of human speed. Now, as you turn up the percentage of time used by the interrupt, I'm only doing 2 voices here. It's taking about 40% of the CPU. As you turn up the number of voices, then main is going to slow down. And at some point, you're going to get to the point where the LCD fails or something else fails, because the delay function, which is soft-coded in part of LCD lib, is also slowed down by interrupts. So at some point it'll fail. Another possibility, now I suggest, if you're good, remember it's the product of sample rate times number of voices that is the performance factor here. And after you get to 4 voices, if you say, well, I can implement 9 voices, how are you going to possibly listen to that and validate it? Why not, instead of implementing 9 voices or 25 voices, one of you will probably do 25 voices. Instead of doing that, why not turn up the sample rate and keep the number of voices limited? So instead of sampling at 8 kilohertz, sample at 44.1. That's standard CD rate. And then implement 2 voices. You can turn up either one you want. Efficiency doesn't matter. Now, but as you go to higher and higher sample rates, it means that you're entering and exiting the interrupt much more often, and therefore the static overhead of entering the interrupt is going to start to matter. The static interrupt for entering, the static overhead for entering an interrupt is about 70 cycles. Takes 5 cycles for the CPU to get into the interrupt, just in terms of pushing the PC and saving the SREG and doing a couple other things. But it takes 32 cycles, takes 64 cycles to save to push all of the registers. And I'm not sure how smart the compiler is. I think it just pushes all the registers, or close to it. And it has to pop all the registers back off again after the end of the interrupt service routine. So as you start pushing a few microseconds between interrupt service routine hits, invocations, you're going to run into the point where you don't have enough time to push and pop all the registers. You can get around that if you're brave. And the reason you have to be brave is that if you turn off the auto register save, does anybody remember what the keyword for that is? I think it's naked. I think you put the keyword naked, or maybe it's raw, I can't remember which, in the interrupt service call, and it does a naked interrupt call which does nothing but push the PC and drop into the interrupt. When you do that, C cannot run in the interrupt. You have to use assembler. Oh! The assembler is not so bad. It's a straight up RISC assembler. You know, it's got the usual vaguely MIPS-like assembler commands. You can write assembler very easily, particularly if you write the interrupt service routine first in C, print out the .lst file, which is the assembler listing, and then just take the assembler and analyze it by eye. You can figure out what it does, then you can compress it and throw away what you don't need. You might be able to get in and out of an interrupt service routine in the raw mode or the naked mode or whatever it's called in about maybe 18 cycles. For those of you who are assembly language adventurous. So, if you go to high rate, high sample rate, you're going to have to worry about interrupt service routine overhead. If you go to high voices, you're going to have to worry about, well, memory use probably, but also about validating that you're actually producing that many voices, because it's going to be just a jumble of sample noise. Any questions?
Can you hear the difference between the 8 kilohertz and 16?
Yeah, I think you can. Can you hear the difference between 8 kilohertz sample rate and 16 kilohertz sample rate? I think you can for a couple of reasons. One is the 8 kilohertz sample rate does have a small 8 kilohertz artifact. And you can hear that kind of whining in the background if you don't filter it. This is filtered. Oh, let me show you that. This has been filtered through a... That's unfiltered. You hear that kind of schnasty background? So, I think if you go to 16 or 32 kilohertz, you're going to get a better background noise. And you get, not only you get better background noise, but you get better, you get less aliasing through the FM modulator, through the FM process, and so you get a little bit cleaner sound. However, remember that if you change the sample rate, the constant for going from F out to the increment is no longer 8.192. It is something else. You have to recalculate that to get the correct frequencies. Otherwise, all your frequencies will be really high. It'll sound like an inhaled helium. Nothing else on lab 3? It's all cool? Nobody started. It's more likely the answer. It's a fairly straightforward lab in some ways. In other ways, I think when you start implementing the Markov process, you're going to have some questions. I've heard some already from people that have started doing that. How exactly do you determine where you are, what you should do in the matrix? Look carefully at the MATLAB code, because I do a couple of tricks in there which I thought made it easier. Maybe, maybe not. Okay, we have a few minutes. Final projects. Final project write-up is due the week of the, that's a little over 2 weeks from now, right? Week before spring break. Spring break is the 16th, I think. So that means that this is going to be due the week of the 12th or so, or 11th. Gasp. So we need 3 pages, 2 to 3 pages, describing what you want to build so that the TAs can evaluate whether it's possible or not. Possible and reasonable. So, ideas. Who wants to share a crazy idea? Oh, come on.
Brain-computer interface using EEG.
Oh, man. Brain-computer interface using EEG. Okay. That is hard for a number of practical and theoretical reasons. One is nobody has the slightest idea what a brain code is.
Yeah.
And they're not likely to come up with although there are some evidences that by putting enough electrodes on somebody's head, about 100, don't do this, that you can tell what word they're thinking of. How is that different from mind reading exactly? So but the potentials coming off the surface of the skull, which are due to electrical activity in the brain, are on the order of a few microvolts. And the resolution is on the order, on the surface of the brain is on the order of a centimeter or so. So your resolution is poor and the level is low. You have to be extremely careful filtering noise, and then you have to figure out how to get something out of the pattern.
Okay.
And certainly it's doable, but it's pretty ambitious.
Right. Well, if that doesn't work, then we were thinking we could still take the EEG and use it as a sleep apnea diagnostic device.
Oh. In that case, why not just put a microphone up your nose?
Well,
I mean, I'm being a little bit silly, but why not?
that does like the snoring though, but
Yeah.
sleep apnea doesn't always involve snoring.
You're quite right. It doesn't always involve snoring. It often does, but not always.
Well, in my case, like I have it in moderately severe, and I don't snore.
Really? So you have So what are you going to measure? So EEG gives you an evidence of sleep apnea.
Because your brainwaves go from the really low frequency delta sleep to the alpha beta, which is the
Alert.
stuff, right?
So you suddenly become alert because you're not breathing and you realize that you're dying.
Right.
Yeah.
Pretty much.
Yeah.
You can also detect that with your cardiac. Your cardio rate,
Because you get a jump in your heart rate.
the temperature and pressure of your breathing, right?
So measuring heart rate is easy.
Right. It's the same, almost the same process as EEG. You just take an instrumentation amplifier.
It's almost the same process as EEG, except the signals are millivolts instead of microvolts.
Right.
And the nice thing about blood pressure and blood oxygenation and heart rate is you can get them from infrared without having to put electrodes on your body. So another possibility would be to build a good pulse oximeter.
Yeah, that's another thing we're thinking of, because it's just some LEDs in a Photoshop. So.
Yeah, the sensors are simple. The normalization is interesting, and it's a good project.
The other tricky thing, though, with that is that sometimes when you have sleep apnea, your oxygen level doesn't necessarily drop. You just get poor quality sleep, right?
But your heart rate probably pulses up and down,
Yeah.
and that you might be able to detect.
Mm-hmm. But your SpO2 doesn't drop below 95%.
It better not, right? Yeah,
Right.
yeah. Interesting. Yeah, if you intend, if anybody intends to connect electrodes to themselves, I want to talk to you a lot before you do this.
Okay.
All right, and particularly your head and your heart. Those being two areas that it's kind of easy to mess up. Now, I'm quite serious. The other thing is, if anybody intend to use high voltage, anybody intend to hook a device to the 110 volt line? Because if you do, I want to be able to verify by looking at the device, bare-eyed, that it is safe. Therefore, I have to see macroscopic isolation between the CPU side and the 110 volt side. It can be a solid state relay. It can be a board with a line drawn down the center, and on this side is high voltage and on this side is low voltage. The only thing in between those, the only thing, is an opto-isolator. It can be any sort of physical implementation that I can verify by eye. Otherwise, I won't let you plug it in. I told this to some guys, I don't know, 3 or 4 years ago, and said, well, we know what we're doing. Okay, but you can't plug it in. They come in the next day, and the board is blown to pieces. There's little fragments of board, little burned components on it, and it's all dangling off the copper. I said, what happened, guys? They said, well, we plugged it in at home. Well, I think we're going to change projects. Anybody hurt? So it turns out that they had built a diode bridge, and the diodes were backwards, and it was a short circuit across the 110 line, and it literally blew the diodes off the board, exploded the board. I mean, there's a lot of energy in a 110 volt line. You know what the short circuit current in your house is?
10,000.
Exactly. Amps. At 120 volts.
A lot more than that, but that's your breaker.
That's where the breakers explode. Right, so now we're talking, 100 kilowatts. Right, that's painful. So you've got to be really careful. Also, if you, on a more practical basis, if you short circuit stuff in the lab, you really annoy everybody around you whose computers crash because the power's off. Saw this happen last year. A guy brought his hot pot in to make tea during lab, and didn't plug it into one of the walls. He plugged it into one of the power strips. It had 10 computers on it, and they're rated about 15 amps, and that hot pot takes about 15 amps, and the computers take about 10 amps, and so he plugs in, boom, everybody's computer goes down. Gee, that's funny. I'll try this one. Right? Right. Boom. So, you got to use a little common sense. But, how do you develop common sense? You make mistakes. Fred Brooks' quote, and I want to put this over the door of the lab one of these days. What is it? Good judgment comes from experience. Experience comes from bad judgment. That's true. You don't know where the limits are until you exceed it. Let's go to lab.